This week, Canada's largest city briefly recorded the worst air quality of any major city on Earth. The fires responsible weren't even close. Their smoke had traveled hundreds of miles before darkening the skies over millions of people. That's why this isn't just another wildfire story. It's the story of why wildfire seasons across North America are changing and what scientists are learning about what's driving that change. For millions of people in Toronto, the warning arrived before they ever saw the cause. The sky took on a hazy gray tint. The familiar skyline faded behind a blanket of smoke. Air quality alerts urged people to stay indoors, limit outdoor activities, and wear masks if they had to go outside. For a brief period, Canada's largest city recorded the worst air quality of any major city on Earth, surpassing cities that are often associated with chronic pollution. Yet, the source of that smoke wasn't an industrial accident. It wasn't heavy traffic, and it wasn't even a wildfire burning anywhere near the city. Instead, the smoke had drifted hundreds of miles from massive wildfires burning across northern Canada, carried south by shifting winds and upper-level atmospheric currents, before settling over one of the country's most populated regions. That alone raises an important question. How can a fire burning in a remote forest affect millions of people who may never come anywhere near the flames? To answer that, we first need to understand what Canada is facing this year. The country isn't dealing with a single massive wildfire. It's confronting an entire wildfire season unfolding across multiple provinces at the same time. By mid-July, hundreds of wildfires remained active, with many classified as out of control. Communities in parts of Ontario and other regions were forced to evacuate as firefighters battled rapidly changing conditions. At the same time, enormous plumes of smoke spread far beyond the burn zones, crossing provincial borders and drifting into the United States. On the surface, this may look like another difficult wildfire season, but scientists say the larger story isn't simply about the number of fires. It's about the conditions that allow those fires to ignite, spread, and continue burning. Wildfires have always been part of Canada's natural landscape. Many forests actually evolved with periodic fires. Lightning strikes have ignited fires for thousands of years, clearing vegetation, recycling nutrients, and creating space for new growth. In that sense, fire itself isn't unusual. What has scientists paying closer attention is something else. The conditions surrounding these fires appear to be changing. Longer periods of extreme heat, more persistent drought in some regions, vegetation drying out earlier in the season, and weather patterns that can transform a manageable fire into an uncontrollable one within hours. None of these factors alone explains every wildfire. Every fire has its own story with different ignition sources, landscapes, and weather conditions. But when researchers examine hundreds or even thousands of fires over many years, they begin to see broader patterns emerging. That's where this story moves beyond today's headlines. Because understanding why Toronto's air turned hazardous isn't really about one city or even one week. It's about understanding how heat, drought, forests, wind, and climate interact in ways that can reshape an entire wildfire season. And that's exactly where we'll begin. To understand why this year's wildfire season has captured so much attention, we have to look beyond a single city and examine what has been unfolding across Canada itself. From the air, the scale is staggering. Across vast stretches of the country, columns of smoke have risen from forests, separated by hundreds of miles. Instead of one massive fire dominating the headlines, Canada has been dealing with hundreds of active wildfires spread across multiple provinces at the same time. Some have remained relatively small, others have expanded into enormous fire complexes that are incredibly difficult to contain. For firefighters, this creates an entirely different challenge. Resources have to be divided across dozens of simultaneous emergencies. Aircraft cannot be everywhere at once. Ground crews often have to prioritize which communities face the greatest immediate danger, knowing that some fires simply cannot be attacked safely under extreme weather conditions. For the people living in those regions, the experience is both sudden and deeply unsettling. Many communities receive evacuation orders with very little notice. Families pack only what they can carry. Roads that normally see little traffic suddenly become evacuation routes as thousands of residents leave behind homes, businesses, livestock, and memories, without knowing when or if they'll be able to return. For those watching from major cities hundreds of miles away, however, the danger can seem strangely invisible. They don't see walls of flame, they don't hear helicopters overhead, they don't watch firefighters digging containment lines through dense forests. Instead, they wake up to a sky that looks different. The air smells faintly of smoke, the horizon disappears behind a gray haze, and their phones begin displaying air quality alerts that seem completely disconnected from anything happening nearby. That's one of the most unusual aspects of large wildfire seasons. The greatest impact isn't always where the fire is burning, sometimes it's where the smoke eventually arrives. Smoke from a wildfire is remarkably efficient at traveling long distances because much of it doesn't remain close to the ground. As intense fires generate enormous amounts of heat, they create powerful upward currents that lift smoke thousands of feet into the atmosphere. Once there, those particles can become part of larger wind systems that transport them across provinces, international borders, and in some cases even across oceans. Scientists sometimes describe this as the atmosphere acting like a highway. Instead of remaining trapped near the source, smoke can enter fast-moving air currents that carry it far beyond the burn zone. The people breathing that smoke may never see the forest where it originated. That's exactly what happened this week. The poor air quality in Toronto wasn't caused by a fire burning on the edge of the city. It was the result of smoke produced hundreds of miles away, transported south under favorable atmospheric conditions before settling over one of Canada's largest population centres. And Toronto wasn't alone. Communities across southern Ontario and even parts of the northeastern United States experienced hazy skies and declining air quality as the smoke plume expanded. In some areas, visibility dropped dramatically. Outdoor events were cancelled, and public health officials advised children, older adults, and people with respiratory conditions to remain indoors whenever possible. It's easy to assume that smoke simply drifts wherever the wind happens to blow. In reality, the process is far more complex. Its movement depends on wind speed, wind direction, atmospheric stability, temperature differences between air layers, humidity, and even the height that the smoke reaches after leaving the fire itself. A small change in weather can send the plume toward a completely different region within hours. That's one reason forecasting wildfire smoke has become an increasingly important part of modern weather science. Meteorologists no longer focus only on predicting where flames may spread. They also model where smoke is likely to travel, how concentrated it may become, and which communities could experience unhealthy air days later. But this leads to an even bigger question. If smoke can travel hundreds of miles because of normal atmospheric processes, why does it seem to be affecting so many more people today than it did in the past? The answer isn't simply that smoke has changed, it's that the fires producing that smoke and the conditions allowing those fires to grow so large appear to be changing as well. And that's where scientists begin looking beyond the smoke itself, toward the forests, the weather, and the climate conditions that increasingly shape every wildfire season across North America. If smoke is only the visible symptom, then the real story begins on the ground long before a wildfire ever starts. Every wildfire needs three basic ingredients to grow: a source of ignition, vegetation that can burn, and weather conditions that allow the fire to spread. Lightning remains one of the most common natural causes of wildfires across Canada's vast boreal forests. Human activity also plays a role, whether through unattended campfires, discarded cigarettes, equipment sparks, or accidental ignitions near developed areas. But an ignition alone doesn't determine whether a fire remains small or grows into a disaster. The deciding factor is often the condition of the landscape itself. Think of a forest as an enormous reservoir of fuel: living trees, dead branches, dry grasses, layers of fallen leaves, even the thick carpet of organic material covering the forest floor. Under normal conditions, much of that fuel contains enough moisture to slow the spread of fire. Flames may move through an area, but they often encounter vegetation that doesn't ignite easily. During prolonged periods of hot, dry weather, however, that balance begins to change. Moisture gradually evaporates from plants. Dead wood becomes increasingly brittle, and the forest floor dries out. Scientists refer to this as declining fuel moisture, one of the most important indicators used to estimate wildfire risk. As fuel moisture drops, the amount of energy required to ignite vegetation decreases dramatically. A spark that might have died out after a few minutes can suddenly become a fast-moving wildfire. And once a fire becomes established, weather begins to take control. Temperature, humidity, and wind constantly influence how a wildfire behaves. High temperatures accelerate evaporation, drying vegetation even further. Low humidity removes moisture from both living and dead plants. Strong winds feed fresh oxygen into the flames while carrying burning embers far ahead of the main fire front, creating entirely new fires well beyond existing containment lines. This process, known as spotting, is one of the reasons large wildfires can appear to advance with astonishing speed. Firefighters may successfully slow one section of a fire only to discover that wind-driven embers have already ignited new fires several miles away. To someone watching the news, it can look as though the fire somehow jumped. In reality, physics in the atmosphere did the work. Researchers often describe these combined conditions using the term fire weather. Fire weather isn't a single event. It's a combination of heat, low humidity, dry fuels, and wind occurring at the same time. When those factors align, even experienced wildfire managers know that suppression becomes significantly more difficult. That doesn't mean every hot day produces catastrophic fires. Nor does it mean climate alone determines the outcome of every wildfire. Topography matters, forest composition matters, recent rainfall matters, human decisions about land management also matter. Scientists emphasize this point repeatedly because wildfire behavior is rarely driven by a single cause. Instead, it's the interaction of many different variables. That's an important distinction. Public discussions often reduce wildfires to one explanation or another. Some argue they're simply natural. Others suggest they're entirely the result of climate change. The scientific picture is considerably more nuanced. Individual fires always have immediate causes, but when researchers analyze wildfire seasons over many years, they begin to identify broader environmental trends influencing how often dangerous fire conditions develop and how long they persist. One of those trends is the increasing frequency of extended periods of hot, dry weather in many regions. Another is the lengthening of the wildfire season itself. In some areas, snow melts earlier than it once did. Spring arrives sooner. Vegetation begins drying earlier, and favorable fire conditions can continue later into autumn than they have historically. That doesn't guarantee more fires every single year. Weather naturally varies from season to season, but it does increase the opportunities for large fires to develop when ignitions occur. This is why scientists are careful with their language. Rather than pointing to a single cause, they examine how multiple factors interact. Weather, vegetation, topography, ignition sources, and long-term climate trends all influence how a wildfire behaves. The weight of each factor can vary from one fire to another. That's why researchers rarely ask what caused this wildfire. Instead, they ask a broader question. It's a subtle distinction, but an important one because understanding the conditions behind these fires is often far more valuable than focusing on any single ignition event. If today's wildfire seasons feel different, it's because scientists aren't looking at one dramatic summer in isolation. They're looking at decades of observations. Every wildfire leaves behind information. Satellites record burn scars stretching across the landscape. Weather stations continuously measure temperature, humidity, rainfall, and wind. Forest agencies document when fires started, how they spread, what fuels they consumed, and how long they burned before finally being contained. Taken together, these records allow researchers to step back from individual disasters and ask a much larger question. Are today's wildfire seasons actually changing across many parts of North America? The evidence suggests they are. Researchers have observed that in numerous regions, wildfire seasons now begin earlier than they once did. Snowpack often melts sooner, exposing vegetation to warmer spring temperatures. As the weeks pass, prolonged heat and limited rainfall can gradually remove moisture from grasses, shrubs, and forest floors, creating conditions that are increasingly favorable for fire. At the same time, some regions are experiencing longer stretches of weather that firefighter dry fuels, low humidity, and strong winds occur together. Those conditions don't guarantee catastrophic fires, but they increase the chances that a fire, once ignited, can spread rapidly before crews are able to contain it. Scientists have also noticed another important trend. Some of the largest wildfires in recent years have become powerful enough to influence the atmosphere around them. The intense heat generated by massive fires can create towering columns of rising air, sometimes forming enormous smoke clouds known as pyrocumulus clouds. Under certain conditions, these clouds can even develop into thunderstorms capable of producing lightning, strong winds, and unpredictable fire behavior. In other words, an extreme wildfire doesn't simply respond to the weather, it can begin to alter the weather immediately around it. That's one reason large wildfires remain so difficult to manage. Firefighters aren't only confronting flames on the ground, they're also responding to constantly changing atmospheric conditions that may shift within hours or even minutes. Even so, scientists remain careful about what the evidence does and doesn't show. Wildfire activity varies naturally from year to year. Some seasons are relatively quiet, others become exceptionally destructive. Researchers don't expect every future summer to break new records. Instead, their focus is on the long-term direction of the trend, and across many studies, the same conclusion continues to emerge. The environmental conditions associated with dangerous wildfire seasons are appearing more frequently in many parts of North America than they did in previous decades. That doesn't mean every fire is unprecedented, but it does mean the circumstances that allow extreme fires to develop are becoming increasingly important for scientists, emergency planners, and the millions of people living far beyond the forests where those fires begin. Perhaps the most important lesson from this wildfire season isn't that Canada is burning. Canada has always experienced wildfires. The more significant question is whether the conditions surrounding those fires are changing and what that means for the future. Scientists don't expect every wildfire season to look exactly like this one. Weather is naturally variable, and no two summers unfold the same way. A cooler, wetter year can reduce fire activity, while hotter and drier conditions can produce a very different outcome. That's why researchers avoid making predictions based on a single season. Instead, they focus on long-term observations. When decades of satellite imagery, weather records, forest conditions, and wildfire data all point toward similar trends, scientists gain greater confidence in understanding how wildfire risk is evolving. For emergency managers, that knowledge is becoming increasingly valuable. Modern wildfire response is no longer just about extinguishing flames after they appear. It also involves forecasting fire weather days in advance, monitoring fuel moisture across vast forest regions, tracking smoke movement in real time, and preparing communities before conditions become dangerous. In many ways, wildfire management has become as much about prediction as it is about suppression. That shift reflects an important reality. As populations continue to grow near forested landscapes, the consequences of large wildfires extend far beyond the areas where they begin. Smoke can disrupt transportation hundreds of miles away. Poor air quality can affect schools, hospitals, and outdoor workers far from the fire itself. Entire communities may face repeated evacuations while critical infrastructure, including highways, power lines, and communication networks, can remain at risk long after the flames have passed. The impact of a wildfire is no longer measured only by the number of acres burned. It's measured by how many lives are affected, how far the smoke travels, how resilient communities remain, and how effectively societies can prepare for the next extreme event. And perhaps that's the biggest takeaway from this year's wildfire season. The smoke that covered Toronto wasn't simply the result of a distant forest fire. It revealed how deeply connected weather, forests, climate, and human communities have become. A fire that begins in one remote landscape can influence the daily lives of millions of people who never see the flames themselves. Understanding those connections doesn't eliminate the risk, but it gives scientists, emergency planners, and the public a clearer picture of why wildfire seasons matter and why paying attention to the conditions behind them may be just as important as watching the fires themselves. If you found this analysis helpful, consider subscribing to the Soccer Clock for more evidence-based stories that explore the science behind today's biggest environmental events. Because sometimes the most important story isn't the disaster we can see, it's the changing conditions quietly unfolding long before it begins.